All right. So we've been doing oscillations for the past week and a half or so we're going to take a step back and start going back through the other content.
Mm-hmm.
Um, so I'm going to go back to what I think is the hardest topic for me, but this is rotation and torque.
Mm-hmm.
Um, so we're going to kind of play with rotation and torque along with energy and momentum today a little bit.
Mm-hmm.
So I'm going to quickly review a couple formulas for rotational kinetic energy and angular momentum. We'll take a look at it for your response, and hopefully you can talk me through it, and I'll kind of help you out as we go, if we need it. So, if we have an object that is rolling, then it would have both translational and rotational kinetic energy. So that translational kinetic energy is a normal 1/2 mv squared. That rotational kinetic energy is going to be the rotational analog, so that's our moment of inertia,
Mm-hmm.
and our angular velocity squared.
Mega.
Right. Okay. For angular momentum, we could say, by definition, our force is equal to our derivative of momentum in terms of time. So then our rotational analog would be the torque would be equal to the change in our angular momentum over change in time. Then I could cross multiply. So this would be our torque times our change in time should be equal to our change in momentum. Our
Mm-hmm.
torque is my displacement cross my force. So that would be displacement cross force times dt. My force is my mass times my acceleration. Um, so this would be mass times acceleration, which is my change in velocity over change in time. And then my change in times will cancel. So that's my displacement cross my mass times change in velocity. Or formula for angular momentum. So angular momentum is RMV if we're acting in a line. And then R cross MV if we're not.
Mm-hmm.
Um, if we take all point masses into account, then this would become in angular form. Our angular momentum is equal to our angular velocity times our moment of inertia. So that gives us two different formulas that we can use for angular momentum. Okay, this is all review, but any questions so far?
Uh, nope.
Okay, so with that in mind, let's go ahead and try it. I've got all of our formulas here. I'm going to quickly drop the formula sheet in the Skype chat because I won't be able to broadcast this and the PowerPoint at the same time.
Mm-hmm.
I'll do it in the WeChat as well. So this is here. Okay, actually, I think I'm just going to leave it on WeChat. That way you can have your phone out with the formulas if you want to.
Yep.
Okay, so all of these formulas that I've boxed in red are formulas that you'll be dealing with your with angular motion. So I've got our centripetal acceleration in angular form, our torque, angular acceleration, moment of inertia, center of mass equation, velocity compared to angular velocity, angular momentum, kinetic energy for rotational kinetic energy, then rotational velocity and rotational displacement, which are all three analogs of our normal translational kinetic energy. So that's actually on the other page. Okay, over here, translational
Mm-hmm.
kinetic energy, and then our translational displacement and velocity equations. They didn't give this one to us, but we could do a rotational analog of our third kinematics equation as well. Okay, so starting with our problem. I'm going to quickly test to see if I can see red. Gets a little bit hard to see, so let me change colors. Okay, that's good. So we've got a 1 kilogram object moving horizontally with our velocity of 10 meters per second. It makes a glancing collision, so that means it's going to hit the bar, and it's not going to stick. It's going to bounce. We make a glancing collision with the lower end of the bar that was hanging vertically at rest before the collision. For the system consisting of the object and the bar, linear momentum is not conserved. Oops. Go back to red for that. Linear momentum is not conserved in the collision, and we have a glancing collision. But kinetic energy is conserved. The bar has a length of 1.2 meters and a mass of 3 kilograms, which is pivoted about the upper end. So we've got a uniform distribution of our mass right now. So that means our center of mass right now is here in the middle. Okay, and the bar swings freely, and after the collision reaches a maximum angle of 90 degrees with respect to the vertical. So that means we swing straight up here. Also, after the collision, the ball is going to bounce off, right? So there should be some angle after the ball bounces off. Okay, the moment of inertia is given. The moment of inertia of the bar is ml squared over 3. And we want to ignore friction. Okay, first thing we need to do is determine the angular velocity of the bar immediately after the collision. What do you think I have to do?
Well, it's kind of late.
Okay, I think you broke up a minute there. Can you say it one more time?
Oh, yeah, it's working right now.
Oh, okay, sorry.
So we're doing A, right?
Yes.
So this time we used conservation of energy,
Okay.
I think.
So this is conservation.
So
You're right.
that's when all the potential energy is converted into kinetic.
Well,
No, that's when kinetic energy is converted into potential and rotational, right?
okay. So if we get to the final point after the collision, then all of the kinetic energy that would have transferred to the rod would be transferred into pure potential energy, right? So there's no motion left in the rod.
Oh,
Okay, so we can do even a little bit more simpler than that. Since we're not looking at a point along the way, we're just looking at the end point where everything is already potential. Okay, so the kinetic energy that the rod will receive, though, is all angular kinetic energy. So we need to figure out how much angular kinetic energy went into the rod. So what's our formula for angular kinetic energy?
angular kinetic is 1/2 omega I omega square.
1/2 I omega squared equals our potential energy. Potential energy is
1 mgh.
mgh. Okay, I need to be a little bit careful here though, because what is my h?
1.2.
So the problem with that is my mass is not at the end of the rod, it's in the middle. Once the ball hits, then the ball doesn't really have anything to do with the swinging motion of the rod anymore, right? So as soon as the collision's over... Oh. Hello, can you hear me? Can you hear me?
Wait, no, I can't hear you.
Okay, cool. As soon as the collision is over, then the rod is just the only thing we're concerned about here. So right now my center of mass of the rod is not at the end though, my center of mass is at the middle. So what should my height be?
It's not 1.882.
It's not 1.2 because my center of mass isn't at the end, it's in the middle.
Oh, it's 0.6.
0.6. So I'm going to change colors again. You've got this, but my height is actually looking at this change in the center of mass.
Mm-hmm.
Okay, that's good. And we are solving for angular velocities. We already have the variable that we need. And we were given our I, so I'm going to substitute for that in. This is 1/2. Our I is ml squared over 3. Omega squared is equal to mg times 0.6. Okay, then we just need to solve for omega. So what do I need to do?
So, and then m cancels out.
Yep. Oh, I can actually... Okay, I'm going to leave this as L over 2 for now. Because that'll give us variables that could potentially cancel, maybe.
So we
And
times
then we'll
2.
substitute in. Okay, so multiply by 2. And then... What else can I do?
Divide by the m l squared over 3.
Okay, cool. So this is... I'll go there for one step. So my omega squared should be equal to what?
m 2 cancels out, so wait, it's over wait, mgl, and then mgl times 3 divided by ml squared.
Okay, so my m's are going to cancel too, so that's mgl over L squared. One of those L's will cancel.
Yes.
Okay, I think I am going to write this out and we'll just cancel as we go. So this will be 3 mgl over ml squared. Okay, so canceling. We've got 1L, 1L, 1M, 1M. Okay, what's next?
Square root.
Omega is equal to the square root of
3gl over L.
3g over L. Okay, now I can substitute. So my omega is equal to root 30. Since we can use g as 10, we were given that in the problem, over 0.6. Okay, now I'm going to assume we do not have a calculator because this is 1987. So I have omega is root 30 divided by 6 over 10, or 30 times 10 over 6. Okay, so this can cancel. So that'll leave me with
5, 3, 50, root 50. Is it? Yeah, 50.
okay. Can we simplify?
That's 2 root 5. No, 5 root 2.
Okay. So I'm going to check really quick. Okay, I'm showing 5 radians per second, so let's see if we can figure out what we did wrong. gravity r length. Ah, I see. This is our total length, not our length over 2 right now. So this is not 0.6. What should this be?
1.2?
1.2. Okay, so I'm gonna do this and multiply by 2 on the bottom. So when I'm dividing by that 2,
So
when we flip and multiply, so that's going to be on,
isn't it then root 25 if we divide it by 2 inside the root?
yes,
So it's just 5.
yes. Okay, what are our units?
Radian per second.
Radians per second. Okay, cool. Any questions on A?
No.
Okay, I kind of confused myself there with the 1.2 versus the 0.6, but we're looking good. Okay, I'm going to copy what we had last time, so we know omega is 5 from now on. Okay, part B.
Determine the speed after the collision. Speed after the collision. Okay. So do we use angular momentum conservation?
Okay, let's try it.
So angular momentum before is just mvr, I think.
Okay, so mv, I'm going to write mv naught. Okay, mv naught equals,
And times r, I think, but we don't know r.
okay, my linear momentum's not conserved. I don't think this is going to work. I think we need to look at energy.
Yeah, so it's like one half mv square is equal to 1/2 mv square and then rotational kinetic.
Okay, so that's all stuff you've given me so far. Okay. So we actually know everything here except for one variable, so let's plug in everything we know. Okay, so this is 1/2, our mass was 1. Initial velocity was 10 squared, equals 1/2, our mass of the ball is, after the collision,
1.
still 1. Our final velocity is what we need to solve for. Final velocity of the ball. Okay, plus.
And then plus 1/2 I is given in here.
Okay, is ml squared over 3.
And then omega is the one that we solved in A.
Okay, was 5.
Yes,
Okay.
and then simplify.
Right, again, we don't have a calculator, so we're going to do this by hand. So this is 10 squared is 100, divided by 2 is 50.
Divided by 250 is equal to v square over 2 plus 25 over 6 and times ml square. But we know m, I think.
Okay, we
It's the
do.
mass of the bar.
What's the mass of the bar?
That's 3 and then length is 1.2.
Okay, I'm going to write that as 6/5, I think.
1.2 square is 1.44. Wait, yeah, but it's
Yeah,
better to write
I'm
it.
gonna keep this in fraction form, I think.
Mhm.
So that'll be easier for us to do by hand.
Yeah.
Okay, so I've got 6/5. Let's go ahead and simplify this part before we. I'm gonna
Mm-hmm.
move this over and simplify. I guess this is
So,
50 minus. If I simplify this, what will happen?
mm, kind of complex. So, 1, 6 cancel out,
Okay.
and then 1, 5 cancel out. So it's like we
Uh,
cancel out in the first part for square.
okay. 1/6 will cancel, but I've got a 25 up here, so both fives are gonna cancel.
Yeah, so
Okay.
we just erase square and then we divide by 6 and 5 from 25 over 6
Okay. So that would leave me with 6 times 3.
times 5,
Uh,
isn't it?
okay. I'm gonna write this out. So this is 6/5 squared, right? Is 6/5
Mm-hmm.
times 6/5. Okay, so that gives me 25, 5, 5, 6, 6, right?
Oh, yeah. So that's 18, so that's 32, then times 2 is 64, and then square root is 8.
Okay,
Yay.
you got me. So VF is equal to 8. What's my units?
Meter per second.
Okay. So far we know VF is 8 and omega is 5. And I'm going to double check. Okay, that is correct. And we'll move to C. Okay, we know omega is 5 and VF is 8 from the previous slides. Okay, part C. I want to determine the magnitude of the angular momentum just before the collision.
So we use conservation of angular momentum, I think.
Okay, what's my definition of my um, angular momentum?
Definition?
Yep, angular momentum is equal to.
Oh, MVR or I omega.
Okay, so I'm gonna stick to MVR, I think, because we know what the velocity is right now, and we're straight in a line at that point.
Mm-hmm.
And I think that's it. Actually, I think we know everything, right?
So it's 3 times 1.2 times 10.
Yep.
Wait, then it's
Oh, sorry, sorry.
um.
Not 3.
Oh yeah, 1. 1 times 1.2 times 10. So that's just 12.
Okay. Tricky part. What are my units?
You just write in. Um, you just multiply the unit from the equation. So kilogram
Hmm.
times meter per second times meter. So meter square.
Okay. Kilogram meters squared over seconds.
Second. Yeah.
Awesome.
And then D.
Okay. Um,